Well, thanks everyone for being here at the very end, and thanks to organizer once again for the invitation. Today I'm going to talk a little bit more about my research work that are based on the tutorial. You'll see a bit of repeated content and reviews as well. So once again, this is with some joint work with Boris Hannon, with my postdoc supervisor, and Lorenzo Noci, who is also here in the audience. So this workshop is about scaling laws. I briefly mentioned this in the tutorial. When you see a plot like this, it is not necessarily that special because, well, it could come from very familiar objects, for example, central limit theorem, because these plots are convergence plots for central limit theorem, right? So I briefly talked about this on Monday as well. If you choose a moment, alpha, you choose a number alpha such that the 2 times 1 plus alpha moment is the highest bounded moment. In this case, the Kolmogorov distance converges with this rate into the alpha, right? So there are many constraints in scaling limits such that determines the convergence rate, right? So central limit theorem, typically you think about this as 1 over square root of n, but doesn't necessarily have to be this way. You can choose arbitrary power laws. You can do this in other scaling limits. I'm just going to give another quick example. So this is an Euler discretization of an ODE, where you have a little bit less smoothness constraint in time, right? So in this case, your time is Holder instead of Lipschitz, right? So, but it's Lipschitz in X. So if you do an Euler discretization of this ODE using this explicit step, and the step is time divided by number of steps n here, you also have a power law, right? And in fact, this power law is because is deterministic, so your convergence like curves are actually even nicer, right? And you can kind of sort of pick and choose exactly what your favorite alpha that you want. And the whole point of doing this type of examples is to try to make this argument that, well, the next time you see a scaling law from a neural network, right? And I once again mentioned this on Monday. We can view this as the x-axis as a discrete index that's being taken to infinity, right? And each point on the plot is a neural network. We can view it as an element inside a space of neural networks, right? So these are different sizes and potentially trained to different times, right, with different data points, but we view them as living in the same space, right? And then we think about this performance metric as a test function of a space, right? So the performance metric's loss is just, it maps, a neural network to a number, right? And then the question is, well, wouldn't the scaling law be just a consequence of the convergence rate of the neural networks, right? So if the neural networks converge at some rate alpha, then wouldn't the test function also converge at some rate, right? So that's kind of the idea that I'm trying to pitch in my line of work is every time you see a scaling law, actually, we should be thinking about, well, can we study the scaling limit? And this will give us, this will really give us a model of how scaling laws are, right? As many speakers have already mentioned, right? So the interesting scaling in scaling laws for neural networks are in width, depth, batch size, or data, number of training steps, right? And we talked about it would be interesting to study the joint limits of all of these, and there are some toy examples that have been studied for several interesting joint limits where you do get scaling law behaviors, and you can create power law models of where the loss behavior in this. But there are some technical challenges, right? So if you want to study a realistic model, it's very difficult to study all 4 types of limits at the same time. So this is why my work, as well as a lot of the existing work, primarily focused on depth and width limits. And as you may have already seen, where data and training remains finite. I'll briefly mention some very weak extensions in special cases where we can talk about data being infinite, but you cannot train, and then there's some limitations, but we'll talk about this. But the nice thing is, as we already know, it's already interesting, right? This is, despite the limitations in this work, we already understand there are different scaling regimes. So we have talked about this already, about the difference between kernel regime and feature learning regime already. So I think this is kind of like a very clean picture that Greg Yang made in his paper, that whereas the left-hand side is an infinite width neural network, right? And the right-hand side is a finite width neural network. You're expecting the infinite width neural network to do better, right, than the finite size. So what is being plotted here is principal components, the first two principal components of the second last layer of the network, right? So whereas the infinite width neural network, which by the way is still capable of classifying state and city, is not using the first two principal components, right? It didn't identify any particularly good features, good directions that clearly separates state and cities. Whereas the finite width network is actually capable of doing this, right? So this is actually, as a lot of practitioners, probably 20, 30 years have known, this is an important property, right? You want to see your network be trained in such a way where it clearly separates, right, different types of data. So this is something that can actually be formalized. So Greg Yang proposed, obviously, the mu-p scaling, but I want to zoom in on exactly what he did here. So for example, for a linear network, and this can be extended to all sorts of different architectures and nonlinearities, et cetera, the key thing here is to observe that the maximal update definition is about how much the next layer's neuron is changing as a function of the previous layer's weights, right? So this is the update, and I specifically want to highlight the fact that it is a picture about neurons, right? It's about how much the HL plus ones are updating, right? It turns out that this, if you can ensure this condition, you kind of have reached a sense of the most amount of update that you can have for your neural network, at least when width is going to infinity, right? So, and then, so Blake and Louis-Pierre had mentioned you can extend this to infinite depth ResNets. So I'm just giving you the simplest case of a linear one hidden layer block ResNets. But you can, and you have a number of choices for the scaling exponents of depth. But the key thing here is each layer's maximal update would need to be slightly adjusted to contribute 1 over depth because, well, you have d layers, and you kind of want them to sum up to 1, right? So that's kind of the main update that you want. You want to adjust. I won't talk about complete feature learning, but there's a similar criterion about like within the residual block as well. So the key thing here, once again, I want to mention this a second time because it is important, is this is a picture, this is a definition that is focused about neurons, right? Right. So whereas I mentioned also on Monday, as well as like a lot of the other talks have mentioned, it's not the only way to view feature learning. You can also think about them as kernels, right? So I want to plant the seed here because we'll return to this towards the end of the talk. All right. You have already seen some of the curves of this type. So Greg Yang has a very nice result. Hyperparameter transfer, it turns out that empirically, and we don't fully understand why, we have some speculations, that the hyperparameters do align quite well, right? So small size neural networks can have an optimal learning rate that is almost the same as a large size neural network. So the behaviors between small and large are quite consistent, right? So this is very good in practice, and Blake mentioned this, like it saves a lot of computing resource. But another subtle thing that we don't fully understand, but is also quite nice about this scaling, that you can also see in this plot is the performance actually steadily improves, right? So the bigger the network, the better the performance. Whereas if you look at the left-hand side, like there's a bit of plateau happening here. So this part, I think, is a bit underrated, like kind of phenomenon as well. So sometimes having the correct scaling is not just about having the best hyperparameter, right? It's also, can your performance improve as you increase the size of the network? Now, I don't have a great theoretical explanation for why this is the case, but this is, at least we do notice empirically that if you do get the correct feature learning scaling, you do have both of these desirable properties. Okay, so as I also mentioned on Monday, my work is not on not all of my work are on mu-p, but a significant portion of my work is on a different scaling limit, where we are increasing depth and width proportionally to each other. And one of the main reasons is that this is not, so this is also a regime that learns features. It turns out that, and we'll see this in more detail later on, that if you increase depth, that kind of makes up for the lack of the hidden layers being updated as well. So there's a bit of a compounding effect with depth, right? So as you increase width, the middle hidden layers weakens, like the amount of feature learning weakens, but if you increase depth, they actually become stronger again, and you end up learning more features as a result. So there's a bit of a compounding here, and in some earlier work, which we'll review a little bit, we showed that it's necessary to weaken the nonlinearities, that we can provide a characterization of the forward pass using a stochastic differential equation, right? And we can extend this to transformers and solving some vanishing gradient stability problems, which actually I'll have some slides about. But the most exciting part, and probably the part I'll focus most on this work, on this talk, is we are finally able to extend this approach to studying training dynamics, albeit only one step of training so far, and I'll talk about how multiple steps would work. So this took a lot of work from Lorenzo and I, and finally we're able to figure this out. All right. So let's briefly do a quick review. So yeah, if you're here on Monday, this is just going to be a bit of a refresher. So if you only have one input data point for now, let's consider the simple case, right? So pretty much the entire SD frameworks contained in this toy example. And if you have IID weights, right, at initialization, you can consider how much the feature kernel updates, right? And in this case, the feature kernel is just the squared norm, 1 over n, the normalized squared norm of a hidden layer, right? Remember, we did this trick where we pulled out a factor of norm squared here, right? And we leave one inside the norm, right? And this guy, remember, is exactly the feature kernel, right? And the inside here is, squared norm of a Gaussian, which, gives us chi-squared, right? So this was the calculation we did on Monday. And we're going to specifically write it this way, once again, because, well, this looks like now a recursion that is a discretization, right? So because, like we see here you have phi L plus 1 is equal to phi L plus something. And that something is small, right? So something is small because it has mean 0, this random term, and variance 2 over n, right? So it's equivalent to think about this, once again, as an Euler discretization, right? Albeit not with the Gaussian increment, but it's an Euler discretization of an SD, right? So anytime something looks like a discretization, right, it's going to converge, right? In fact, actually, I would argue that is the same behavior, right? Convergence is merely the same thing as discretization, right? It's just realizing something on a computer, right? Discretization is, right? So anytime we think about scaling limit of a neural network, we can also think about them as a discretization of the limit. So in this case, there's kind of an obvious discretization happening here, right? And the other thing I want to highlight is step size is 1 over width, which is very natural, right? We have a scaling that this is kind of given to us and then has a natural step size of 1 over width, right? And therefore, the total depth time, right, which has been used by Blake and Louis Pierre as well, is slightly different than theirs, which is depth to width ratio, right? So the step size is not 1 over depth, but it's 1 over width. So we have a depth to width ratio kind of depth time, right? So this is, besides that, it's very similar ideas about thinking about depth. And the main difference here is we're thinking about kernels rather than thinking about neurons, right? So once again, there's a difference between neurons and kernels here. All right. I mentioned last time you can extend this to multiple data points. So if you have like, H1 would be like hidden representation of a dog. H2 can be hidden representation of a cat. So and so on. And then you can write down as matrix form SD because now the covariance matrix is now a matrix, right? So now feature kernel is now a matrix. And this matrix, obviously has multiple entries, and you can still view this as a discretization of SDE, once again with same step size. Instead of now square root of 2 phi, you have this coefficient, right? So this is like a flattened local coordinate version of this, right? So you have this coefficient. I'll briefly talk more about this later, but for now, it's good enough that we can derive the coefficients of this. And similarly, we can activation functions, right? So you can add activation functions in here. So I also briefly mentioned on Monday that if you do not weaken activation functions, right, you get some pretty poor numerical behavior. I'll show an example in transformers later, but it turns out that if you were to weaken, for example, ReLU at exactly this slopes, this type of slopes, right, I talked about on Monday, this is exactly the right scaling because, well, you match the natural step size of the random weights, right? So this is, you can imagine there's some power here n to the power of p that you can set the p, right? So how do we set the p is, well, we want the scale of the activation function's contribution and the weights to match, right? Why do we want them to match? Is, well, you want the limiting model to be able to capture finite effects, right? You kind of want well, for example, like, if this is weaker, right? So if this is power like, greater than p is greater than 1, for example, in the limit, you would only have the weights left. You will have a linear network, right? So you will lose the effect of the activation. Similarly, on the other hand, if it was stronger than this, and you can change the time scale so that only the activation survives and it's not blowing up, but then you lose the weights, randomness, right? So there's a sense that trying to keep as many terms as possible gives you a better model of the network. And in fact, actually, I would argue that when people talk about maximal update, there's a sense that like mu p is doing something very similar. You're trying to keep as many terms in your update equations as possible, right? You're trying to make sure that as few finite size effects vanish as possible. In this case, we're trying to do the exact same thing, right? And we'll see that this is actually this will actually yield a very good model. Yep.
Can you remind where the small b comes from?
The small b comes from. Let's see what is the effect of the activation functions. How should I explain this? Sorry, I'm like blanking out here because I don't have the slide on this. But you can imagine so you can imagine if you have in the infinite width limit, right? So you can imagine that if you take the expected value of the kernel of the next layer, right? You're going to get something, and basically the idea is that, well, we should be getting something that looks like b of phi l divided by n plus some lower order terms, right? And then this calculation, I mean, you can expand this, and you can expand this to basically get 1 over n of phi of hl plus 1. Let's call this alpha beta. Right. Yeah. So you can do this calculation, and remember these guys are Gaussians, right? So these guys are Gaussian. So we're kind of doing and also like this is an average, right? And then there are ID samples. Yeah, they're ID samples. So you can kind of move the expectation inside, right? So what you end up computing is something like the effectively, what I would call H alpha, H beta. So it's kind of like a Gaussian expectation where H is a Gaussian with variance phi L, right? So whatever activation you have here, you can try to compute this, right? For ReLUs, you have closed form formulas for this. For polynomials, obviously, you can also have closed form formulas for this. So for things that you're doing something like a Taylor expansion of a smooth function, you can do this as well. So this actually, I'll show you on the next slide that you can do this for smooth functions. But basically, this is what B is. So B is kind of this like expectation, I guess, subtract phi L. Yeah.
So essentially, it's like a drift that is being by the nonlinearity.
Yes. That's exactly it. Yeah. So the nonlinearity the drift comes from exactly the fact that you're computing a second moment of like ReLU Gaussians, basically. Yeah. Yep.
For instance, in the specific case of
Yeah. You get a slightly ugly formula. Yeah. So B of phi is equal to, so you have, let's call this B of phi the alpha beta entry. So you first take out the variance components, and then you have a correlation component. Yeah. And the correlation component looks something like a constant. I think it's like C minus some constants divided by 2 pi. You have 1 minus rho alpha square root. Yeah, so it's not like super intuitive what these things are doing, but you can write these down in closed form. I think the main thing that is most intuitive about this is that basically it turns out that this is always positive, so it kind of always pushes the rho towards 1, and it kind of obviously vanishes at 1, so you cannot push it any further. So it kind of pushes, so the activation function is kind of always pushing the correlation to be closer between different points. And you think about it, it kind of makes sense, right? You pass through the data through the same weights, and the nonlinearity kind of like is a bit of always coupling things a little bit more, right? To kind of bring things a little bit closer. Yeah, so this is, yeah, so you can calculate these things explicitly, yeah. If it's linear, you just don't have this term, yeah. You just only have the noise term, yeah. And the noise term, I think, is, if you look at the correlation level, it's symmetric between positive and negative directions. I don't remember exactly what the curve looks like now, but it's like, it's not doing the same thing that the drift is doing, yeah. Yeah. Yep. Okay, sure. Yeah. It's good? All right. Okay, let's see. Yeah, so you can kind of interpret this as kind of a downscaled version of the Cho and Zal kernel, which is very similar to the formula I wrote down, if you're familiar with this. All right. So I also wanted to give an image of what the modified activation functions look like. In this case, it looks like with ReLU, you change the slope that's closer and closer to 1. Right, so I briefly talked about this before. So you can kind of imagine a leaky ReLU that's, you can either interpret this being more or less leaky, but it basically becomes closer and closer to 1, right? And the reason is, once again, right, you're going through D layers of ReLUs. You kind of every time you go through the same thing more, you kind of want to weaken this further, right? So this intuition about scaling this, right? You have more things, right? You're iterating more things. You kind of want to weaken this. For a smooth activation function, we're going to zoom in around 0, 0, roughly, right? So you can do this for sigmoid 10H and any smooth functions that you want. So we're going to zoom in further, and this will also make the activation function more and more linear as we increase the depth and width of the network, right? And what ends up happening here in the limit, I briefly mentioned, is you end up only caring about a Taylor expansion of this activation function. You end up caring, I think, about like the first 3 derivatives, right? So there's a sense that like you can do this drift computation for the first three like moments, essentially. So that is also doable. So you can calculate the limiting kind of drift for any type of activation functions that you in these two classes. Okay. I also briefly want to talk about some of the remarks. I think I briefly mentioned this during Monday. You can indeed sample from the neural network given the covariance SD, right? So for example, if you want the output, right, you're just going to sample the covariance SD at the terminal time, and then you sample Gaussian, right? You can do this for hidden layers too, right? So there's a sense that this covariance SD actually captures everything we want about the hidden neurons in the forward pass. Yep?
So, like F as a marginal, though, would I guess be non-Gaussian? It's a mixture of...
That's right. That's right. That's exactly correct. Yeah. That's exactly the way I think about it. It's a mixture of Gaussians, and the mixture distribution is exactly the phi distribution. Yeah, so the mixture comes from the SD. Yep. Okay. Monday, somebody also asked me about how big the networks needs to be for this to be a good approximation. So this simulation used, I think, width about 150. I think 100 didn't look as good. And then what these plots are is they some 10,000 samples of random neural networks at initialization. And I took what the empirical measure of this entry, and I plotted a empirical histogram of the phi entry. And then I have the red curve here are samples from the SDE, and I did a kernel density fit. And they overlap pretty well. I think I did not measure the Kolmogorov convergence rate, but I think it's like 1 over square root of width type of convergence. So basically it's quite good. I will add a small caveat that it does depend on the coefficient choice you choose for the ReLU slope. So if the ReLU slope converges to 1 at a very slow rate, then this would be worse approximation. And the reason to think about this kind of you're increasing the step size for Euler discretization. You want a small step size for it to be a good approximation. So that can affect things a bit. I think the parameters I use here are the slope is literally just like on the order 1. So I did I think like C. I call it C plus minus, right? So it's 1 plus 1 over square root of n type of thing. So if you increase that, you're going to have to increase width a bit for the approximation to be good. One nice thing about this is that it turns out to be a very good model of correlations concentration near 1, right? So this I briefly mentioned on Monday, right? This is a regime where you have vanishing gradients. So you can model this quite well using this approach. Whereas if you take the infinite width limits, this is the neural tangent kernel estimate, which is concentrating, right? So and you get actually a point estimate, which is you're not going to capture this kind of random concentration here towards 1. This is also a good time to also highlight yet another difference in this regime is that, as you can see here, the covariance is not concentrating, right? This is a random variable in the limit, right? In all the other infinite width regimes that we have seen so far, this is a deterministic variable, right? So the fact that it's not concentrating is very interesting, and I would argue that this is yet another term, essentially, that we're keeping approximating finite-sized networks, right? Because as you see in the empirical histograms, right, finite-sized networks have a random kernel, right? Have a random covariance kernel, right? And then we are actually modeling that randomness, so we're capturing that effect. So this is very cool, yeah?
Do you think a similar story would hold if you thought about the kernels as random objects when data is sort of comparable to which or something? So it's like here, like you have a story of F as a mixture of these covariance kernels or GPUs with covariance kernels that are themselves having a random distribution.
Yeah.
I guess one problem I've always run into in this, like, if data's large, is
Yeah, that's a great question. I actually will talk about that very soon. So basically, you are right. So because it's random matrix, data is very large, then the spectrum actually is poorly behaved, right? So you have to rescale things. Yeah, so there is a way to rescale things, which is not perfectly satisfactory. So it's a random matrix theory type result, but I'll show you in a bit. Yeah, that might answer your question. Maybe you in front first? Yeah. Yeah.
Do you have any intuition for why it is correlated with 1 and not anti-correlated, for example, with -1?
Oh, yeah, this is exactly what I mentioned. The drift term pushes everything towards 1, right? So the drift term, like it's...
Does it make it more linear?
Yeah. So the drift term is basically always positive for correlation. If you write down the SDE for just the correlation by itself, yeah, so it's always pushing correlation up. So that's why it's going towards 1. If you look at just random, and you run it for a long time, I actually think you get both. It looks pretty symmetric. Yeah.
When you're talking about the correlation being 1,
Yep.
leading directly to the vanishing gradients, I thought it was fine for the correlation to be 1, so long as your correlation map has gradient ones in your perturbations.
Yeah, so it depends on the specific situation. So I think this is mostly about the type of activation functions that you use in the network. Sometimes you can get different kinds of instability for this, but certainly I think it's literally on this slide. You see for transformers here, so if you look at the weights of queries and keys, these are inside the softmax. And you can see that these networks here, we'll see the green and the purple curves here, the gradients are vanishing across different layers. Probably even worse in the pre-layer norm case, where some earlier layers actually have non-vanishing gradients, right? And then somehow the later layers are vanishing. This is probably even worse because they're on different scales. Yeah, so essentially, the long story is that basically it depends on the architecture of the behavior, but I'm using this as like a particular kind of a useful example to argue that, okay, you probably don't want correlation to be near 1. Yeah. Okay. Yep.
If you write out the full NTK,
Yep.
can you say kind of what shaping does? Like, I think I'm going to ask you,
Yeah.
is the dominant contribution from the linear component if you do shaping because you're downscaling the kind of like...
It's a great question. We're able to say something about this, but essentially they're on the same scale.
Okay.
Yeah, so both the linear and the nonlinear terms contribute. Yeah. I don't think I have the formula for the nonlinear case in here just because it's too long, but the short version is you get more terms in the SD. Yeah. And they match on the scale. Yeah. Okay, great questions. All right. Okay. Yeah, so this is the part I was, Blake was asking about. What happens when you increase the number of data points? In a random matrix theory setting, like this is something that you want to analyze because you can talk about the spectral distribution of this covariance matrix. This is something we can analyze, but only in a linear network, unfortunately. The nonlinear case is quite a bit more complicated, and I'll actually explain why. This matrix diffusion coefficient is very special. Turns out, if you stare at your equation long enough, that you'll figure out all the secrets in your equation. Turns out this is a Riemannian. Turns out it comes from a Riemannian metric on the manifold of symmetric positive definite matrices, and it arises from this following symmetry. Right, so almost a lot of Riemannian metric structures comes from symmetry. Right, in this case, the symmetry is if you were to multiply a full rank matrix either on the left side or the right side of kind of a sample from the SD, right? So the p tau is kind of like the path kernel of the SD, and then it's equal in distribution to if you were to multiply this at initialization, right? So you can kind of conjugate either the initialization or at the end of your SD, right? This is equal in distribution. This is very much arising from the fact that the matrices we use are Gaussian, and as you might expect, this looks like your affine conjugation is invariant. It fits very nicely with the affine invariant metric, and this type of property is very nice because, well, without loss of generality, we can kind of start the diffusion at identity, right? And we just conjugate back the term kind of at the end, the initial condition. And it turns out that this cleans up the analysis quite a bit. And the other nice thing about this is you can kind of, at any single point in time, you can kind of diagonalize your covariance matrix for free. You can kind of easily analyze the eigenvalues. This is very much the same. If you're familiar with random matrix theory, this is almost the same structure of analysis as for GOE and GUE matrices for Dyson-Brownian motion. Essentially, the eigenvalues and the eigenvectors are decoupled, right? They are now independent from each other because of this orthogonal invariant structure that we have. And this is almost the classical result that you get as a result. You see, you can get a SDE, first of all, in terms of only the eigenvalues, right? We don't care about the eigenvectors because they're independent and it's just random, right? They're random orthogonals, right? So in this case, we can just write down a marginal system on the eigenvalues. And if you replace all the red terms here with 1, this is exactly the Dyson-Brownian motion for the GOE matrix, which Blake introduced. And that will give you the semicircle law type of behavior. So this is different. These eigenvalues are always positive, first of all, right? So this is also kind of geometric Brownian motion rather than regular Brownian motion. So this is why the paper, which should be archived literally tomorrow, is called the geometric Dyson-Brownian motion. And the interaction term is also kind of scaled up by eigenvalue squared, right? So this is but the thing is, as soon as if you're working in random matrix DB before, if you saw this, you're like, okay, well, we're gonna figure this out. Right, this is an exciting object. There's lots of things we can do with this. It's fairly tractable to analyze, and indeed we can. And the scaling we need to rescale if you want to take the number of data points, which we call m, to infinity. is we need to do this time change. We need to kind of, we need to slow down time by a factor of m, right? So this corresponds to maintaining this ratio of depth data divided by width to be some constant, right? So let me briefly comment a bit on this ratio. This is not the most satisfying ratio that I think one can take because maintaining this means is very far from practice, right? So Sam briefly mentioned yesterday that in practice, the compute optimal regime you want to train at is when the number of parameters is proportional to data, right? In this case, we're far from that. We have far fewer data than the number of parameters. I have some speculations on why this is the case, but probably mostly have to do with the fact that what is the number of data points that you're tracking? In this case, if you want, we can only track this many data points. If you want to train with more data points, potentially that's not problematic. But this is, if you want to care about how many we can analyze at the same time, this is probably the scale that we can really do. Yeah, go ahead. This is the number of data points well, we're at initialization still, so I guess there's not a huge difference. But if you were to care about like what happens after training, I think the issue is we may need to track the history like the DMFT equations do, right? Hence, it's really about the total number of data points that you have, right? So rather than just batch size. If you are capable of modeling the training dynamics in a Markov sense, where you can kind of forget the previous data points that you have used, then this is about batch size. Yeah, so you will be correct. So as far as our works go, I don't think we have been able to overcome this challenge yet. Yeah. So this is I would say one of the major challenges of all the modeling approaches so far for neural networks is that we have yet to come up with a Markov system, that Markov limiting training dynamics for this. Yeah. Okay. I will briefly mention that Boris had a couple Bayesian. Actually, there's one more recent one I should cite. The setting that also found this ratio. So it's not just for random matrix theory, albeit you can probably argue that it's directly connected. And then we can now analyze the empirical spectral distribution, right, under this scaling. And then we're going to look at, so Blake briefly mentioned the Still-Just transform. We're going to look at something that's very similar to the Still-Just transform called the T-transform. Just placed a little bit nicer. You can actually still work with Still-Just, it's just formula's longer. But basically, you have an extra x here on top, right? So this is like an extra factor of eigenvalue, right? We talked about geometric, Dyson-Brownian motion have an extra factor of eigenvalue in there, so does this here, right? And the limiting distribution, the limiting T-transform, first of all, solves a Burgers type equation, right? So this is almost a Burgers equation. In the GOE case, it's literally the Burgers equation, so you don't have this extra z here. And then, if your initialization is the identity, right? So your initial distribution is direct delta, then you can solve this. You can convert this Burgers equation into a self-consistency equation or fixed point equation. It's very annoying that this guy doesn't really have a closed form formula for this. There is a way to write this. Sorry, this is also called the free log normal. There is a way to write this in terms of a free additive convolution of two distribution of a exponential of a semicircle and uniform. But if you guys know, free additive convolution is also a fixed self-consistency equation. So it's not like that perfectly closed form. But either way, if you care about the actual distribution of this, you can actually just do what's called a free multiplicative convolution between the initial spectrum and the free log normal spectrum, right? So this is kind of nice, right? So remember, we can start at the identity, but we don't have to forget about the initial kind of spectral structure. So that's pretty cool. What does this distribution look like? Is that it's almost Marchenko-Pasteur. If you do a kind of small time expansion of this, it looks like this is the first term that comes out. This is very formal. It's like it doesn't have the same support, but but it almost looks like Marchand capacitor except x squared, right? So it's not normalized even, right? So this is the plot. Yeah, as you can see here, this is the empirics look very good if you do fixed point iterations on this. So if this is the red curve is just doing fixed point iterations. The blue curve is here, is this approximation using kind of this weighted Marchenko capacitor. And you can see here the blue curve is not going to integrate to 1 because of this weird normalization happening here, right? But I'll briefly also mention that you can actually calculate the theoretical support. That comes from just some complex analysis. It's not too hard. So we can study the the limiting spectrum of this kind of stuff, albeit still constrained to fairly simple case at the moment. So if we want to do this for example, like nonlinear case, we really do have to handle the fact that eigenvalues and eigenvectors are dependent on each other. So that's kind of the main challenge here. But I'll also talk about what happens in one step of training because, well, this doesn't prevent us to do training. Yep.
Is there any like large tau asymptotics? Which is the opposite.
I guess it depends on how you scale it. Yeah, probably. Yeah, I think. Yeah.
I might have seen it somewhere. I'm not totally sure, but the free log normal at like long, or like large aspect ratio or something is like heavy tail.
Well, it's heavy air tail for sure. Yeah, for sure. Yeah, you can probably calculate what the tail looks like as tau goes to infinity. Yeah, I'm not sure how I would do this, but I'm sure it's doable. Because, well, actually, let me take that back. It might be even easier to use the form of the free additive convolutions because you just have a bigger semicircle, do a free convolution with a uniform. So that might be easier to analyze, right? So it's just a bigger semicircle, and then you do an exponential push forward. Yeah.
Yeah, I have a related question.
Oh yes, go for it.
Sorry, because in Marchenko capacitor, what you have in the lambda plus minus is instead of lambda, you have that gamma, which is the dimension to sample size ratio.
Yeah.
So is there a way to interpret this lambda somehow?
Kind of, right? Because tau here is roughly like depth data divided by width, right? Divided by 1 plus depth data divided by width. So there's a bit of that, but it's not like so obviously directly related to like sample to like dimension ratios. Yeah, but it's kind of related. Yeah.
Because it feels like if you take the intuition from Marchenko capacitor, then the interesting regime would be what was mentioned.
Yeah.
Tau to infinity.
Oh, I see it. Yeah, I'm not 100% sure actually. But this is let me briefly mention this approximation only works for small tau.
Right.
So this is not the correct support if you have large tau. Yeah, so this is not. So we have a closed form formula for the support. It's a bit longer, but yeah, I'm pretty sure it would go beyond kind of like whatever is shown here, like kind of like 2 and 0 type of thing. Yeah. Okay. All right. Okay, I was promised to talk about this. So what happens when you want to extend to training, right? So this is the most exciting part of my recent work. And the trick is that instead of you treating your weight matrix as IID Gaussian, you can actually condition on all the dependence structure that you have used, right? And then if you condition on here, phi and g are intentionally the same notation that Blake used for the forward activation and backward activation, right? These are exactly the objects that the weight matrix will multiply, right? So remember, in the forward pass is W phi, in the backward pass is W transpose multiplied by g, right? So it's kind of like this is exactly the kind of the ways that this weight matrix have been used in the past, right? So if you condition on exactly how this weight matrix have been used in the past, it turns out that all the dependence terms, right? So these terms are quote unquote measurable by the conditioning, right? So what that means is these are dependence structure. These depend on the things you have condition on. And then you have an extra term. So this is very nice. There's different ways to write this lemma, but this is a very nice way of writing it is that you really can think about this part that you have yet to use as an independent copy of W, right? So you really do have, in some sense, still an IED Gaussian matrix that lives inside this trained matrix here, right? The matrix that you have used. You just have to isolate which part that is IED Gaussian, right? I should give a shout out to Cedric Gerbelot, who taught me this technique, and he wrote a very nice paper deriving a rigorous version of DMFT equations. And in that setting, it was essentially, this is the core like mathematical technique in there, and it really is the same for our derivations. Okay, so how do we use this? So we can consider the first backward pass. Once again, a toy example of a linear one-sample network, which we can extend, but this will get the point across. So we think about this forward pass H, right? And then we think about this backward pass that's defined by square root of n multiplied by the output Jacobian to H, and it has the backward pass has this type of recursion, right? So we're going to condition on all of the forward passes, right? Because if you look at the graphical model here, right, the issue is that, okay, if you ignore the backward pass, the forward pass looks like, okay, from HL to HL plus 1, you inject some noise from WL, and then that's what makes it look like a Markov chain, right? And that's how we're able to do all the analysis beforehand. But if you do the backward pass, well, this is a problem, right? Okay, well, HL feeds into here, goes into WL, and then goes into HL, GL. It's like, it's a whole mess, right? In graphical models, if you want to get rid of connections that you don't want, right, the trick is to just condition on them, right? You condition on these nodes and all the HLs, and all the connections disappear, right? When I say disappear, it's not at zero cost, of course, right? But certainly, you don't have to worry about these connections after you condition on them. So what is the cost? The cost is basically WL is no longer IED Gaussian. That's the cost, right? So the cost is this. Right, so after condition on HL plus 1, right, we're going to actually end up getting a component that is no longer Gaussian, and hence is exactly this part. And then you still have an IED Gaussian part multiplied by the orthogonal projection that is not used, right, of this. Right, so you're now separating two parts. Right, so in the forward pass, you only separate into two components, right? Either you have used or you have not used. Sorry, in the backward pass here, first backward pass. So note this conditioning essentially makes the backward pass looks like a Markov chain, where all the randomness will come from the new W tilde here, right? So you can really think about this as an independent copy. Okay, so in the linear one sample case, I want to do a quick calculation, right? Since you guys are familiar with the forward pass calculation looks like. It so happens there's a simplification. This part you don't have to worry about. It's not super interesting. But the whole point is that you need to also care about this inner product of a forward and backward pass. And then you can, this is kind of a necessary condition. You'll see that it is required. But basically this guy is theta 1, right? It's not going to infinity and it's not vanishing. And this gives us a backward recursion, right? So basically, I just plugged in the, what do you call it, the decomposition using conditioning of WL transpose here, and it gives us some nice forms. And you see QL appears here, and then you can see like phi L appears here, and then GL appears here, right? So GL is the backward feature kernel, right? So this is an object that Blake has also described before, right? So you can now see that right away. This is immediately very interesting, right? So we have a recursion of GL that now depends on Q phi, which we both know already, right? GL itself, which is fine because, well, GL plus 1, right? We can recover this recursively, and then some random term, right? So this is now a random term that is independent of everything else, right? So we actually have this SDE structure, right? And it remains to basically, finish this calculation and basically say, okay, well, you can do this calculation and see what these terms look like, right? And it looks like kind of what do you call it? I'll just rewrite this form, and it looks like this guy looks like a drift term, right? And this drift term arises from the random weights. Actually, this is not there's no nonlinearity in here yet, right? And you get a drift term, and then you still get a diffusion term And notice the diffusion term looks exactly like the forward pass, right? And it turns out it's exactly the same as the forward pass. But basically this guy is new because this is due to conditioning. This is due to the fact that we have already used some subset of this weight matrix. Okay. So yeah, so this converges to an SD, or you can view a discretization SD. I only want to highlight a small caveat is that this is going backwards in time, right? So when I say backwards, I just mean this is the right-hand Ito integral. So Ito, if you're familiar, basically there's some convention you have to choose for the stochastic integral. The main reason I mention this is that if you're familiar with mathematical finance, this is not what they call a backward SD. So very unfortunate naming convention-wise. So it's not exactly the same system. This is literally Ito integral going backwards. That's the only distinction I want to make. All right. So yeah, remark is that we really now can do calculation without IID weights, right? So IID was never a constraint in some sense, right? It made the calculation harder and longer, right? But it's not fundamentally impossible to work with dependent weights, right? So I've received this feedback for many years about like, okay, well you can analyze initialization. How can you analyze training if you need like IID Gaussian weights? Turns out this is not true, right? Turns out you can handle this with just a lot more work. All right. The neurotangent kernel has an interesting form if we normalize it by depth. So Blake earlier talked about this. Neurotangent kernel is exactly this sum. So I have, but if you see, this sum is from 1 to d, really actually probably from 0 to d, and then basically, if you take the limit, it actually looks like an integral, right? So the neurotangent kernel essentially is entirely described by the SDE systems that we have, right? So to your earlier question, if your SDE system has both activation components and random weights components that are on the same scale, they contribute at equal scale basically. So you're not dominated by either weights or activations. Yeah. So you can make this balance each other out. Yeah, in general, Q tau is not constant. So this was just a special case. So if you have a nonlinear network, I think it's already not constant. Together, it satisfies a system of backward equations. So with drift terms from the drift terms from activation function. So I just want to give you an idea what the general case looks like. So we have one SD going forward and a system of two SDs going backward. Okay. So to study one step of training, we actually still need to set the learning rate, right? To set the learning rate, actually, it's surprising. Turns out to be surprisingly straightforward. Is that, well, if you take continuous time, this is literally equal. Basically, the update is learning rate multiplied by the neurotangent kernel, roughly speaking, right? And multiplied by the residual, right? And you have more data points, you can add more stuff. So naturally speaking, your neurotangent kernel is already on the order of depth. You want your learning rate to basically balance it out such that your update is also a balanced scale, right? So Louis-Pierre has mentioned lots of constraints that require the update to also be stable. So this is exactly the scale that we choose, right? We need to choose our learning rate to be 1 over depth, right? Or more precisely, some constant eta base divided by that. Okay. I want to note this as it's actually very different from the mu-p prescription. So mu-p also has, in the case of IID Gaussian initialization case, right? So in some ways, the weights are on the same scale, IID Gaussian 0, 1, right? But somehow, you actually need to choose a learning rate to be eta base multiplied by width, right? You want a learning rate to be increasing as the network gets bigger, whereas our scaling requires the learning rate to be smaller as the network gets bigger. So right, it already looks quite different from mu-p, right? So this is already very interesting, this kind of prescription, right? And the way to analyze this scaling is you want to look at how much the feature kernel updates, right, from one step of training. And to do this, you can separate this into three terms, right? Because it's just inner product. You take a difference and then you get 3 terms, right? So there are two types of terms, right? These two are symmetric, essentially. So if you have more than one data points, these two are kind of symmetric elements of a matrix. But now you have one type. We're going to call this type of kernel R phi. And we're going to call this guy phi dot. I don't know if this is the best naming convention, but this is the best we came up with. So these, if you analyze this guy, we can actually calculate exactly how much the feature kernel updates. It turns out that just like the backward pass, we're also going to need to handle a cross kernel. And this cross kernel is the change of your hidden layer with the backward pass. That's add initialization, right? So this once again is yet another kernel that we need to handle. I'll just give you a very brief idea of how this derivation works. It's the same thing as a backward pass, right? So we're going to look at, for example, delta HL, how this changes, right? And then delta HL can change from two sources, one from how much the weight matrix change, which is the first term, and one from the previous layer's delta HL changes, right? We're not going to keep expanding delta HL because, well, it's sufficient for us to write down a recursion, right? So we're gonna only look at the first, what this recursion gives us. And it turns out that the first term is actually lower order, so we can actually throw this out. This is very interesting because in MuP, this first term is what drives feature learning. For our system, this term is actually lower order. And what drives feature learning actually arises from W's dependence on kind of the past terms, right? So when you condition on both the forward and the backward passes, you get a bunch of terms that comes out of this, right? So you get these three terms that comes out of this. And that is what gives us feature learning. So it's very interesting. Like it actually comes from different terms, right? And the terms end up looking kind of similar, and I'll show you in a second. But basically, you see here, this at the end of the day, we just care about the inner product of this guy. So now you care about inner product of this three terms. So you need to calculate a total of 9 products. And this is essentially why this work was long. Essentially, you have many terms that show up here, and you just need to calculate the product of all of them. But if you expand this, you do get a recursion for phi dot L. The final formula looks a bit complicated, right? And this is just the linear one sample version, right? So I'm already trying to hide as much of the complexity as possible. So all of these are scalar SDs. So it's a system of 3 SDs going forward. And the main thing I want to highlight here is the first guy, this RG kernel that we talked about. This is the cross kernel between the change in H and G. This is actually the kind of form that you see driving feature learning in MuP as well. It does not happen in the same place, right? But the formula looks very similar. And actually, if you integrate this kind of looks like a partial NTK type of thing. It's not exactly it, because if you increase the number of data points to beyond more than 1, it turns out these two don't have the same indices. So it's a bit strange, but it behaves kind of like a partial NTK. I want to say that the key thing here to take away is not so much the specific formula, is that if we converge to the SDE, then we know that the current scaling of learning is stable, right? What that means is we know that for a fact that we're not expecting any numerical behaviors to go wrong as we increase the size of the network, right? We're not expecting anything. It should simply scale. And we do have the full nonlinear version of this. I do very much expect this approach to work for multiple steps. We just kind of need to do the work. And because this work was already quite long, we decided to cut this off here and write the first paper about this. But we very much expect the same procedure to work inductively, which is essentially what Cedric did for his paper on DMFTs in a slightly different setting, but very much similar techniques. So we very much expect this to work, albeit we're just going to get a lot of SDEs, right? So we're going to, every iteration of training is 1 forward pass and 1 backward pass, right? So we think that, and then you see we have 1 SDE going forward, 2 going backwards, and then 3 going forwards, right? We expect to have 4 going backwards, but I think that should be as much as we get. It shouldn't be more than 4 SDs for each forward and backward pass, but it's like, it should look something like that. Okay. One of the most interesting empirical questions you want to ask probably is, does this transfer, right? So this is a preliminary experiment, and I'll add a small caveat that the input-output layers need to be handled slightly differently. So this is also the similar in Louis Pierre's talk. Yes, but for most of the hidden layers, it transfers quite well, right? This is a prescription for all of the hidden layers. Preliminary, right? I would like to test this on bigger models. This is tiny, right? You're looking at the smallest model on here is width 20 and depth 2, right? It's not big at all, but I should highlight that even in μp, you actually don't expect a model this small to transfer, right? In μp, you actually expect a model to be like, you want a model to be like probably about width 100 before you start seeing transfer behaviors. So I am hoping to show that empirically, this actually transfers better than μp, but this is purely speculative. I don't know, but the reason why I'm speculating is in some ways we're keeping more terms than μp is, right? We're keeping the randomness from all the kernels, right? In μp, all the kernels concentrate, right? And in our case, none of the kernels concentrate. So we're hoping that this is a better approximation of finite size networks. Yep. I did, yeah. You see, every time I double width, I actually double depth as well. So I maintain the same ratio, right? So this is slightly different than the case where if you use ResNets, where the depth and width can be scaled separately. In this case, they have to be scaled proportionally. Yeah. I do want to end up also highlighting something very important. So this I briefly mentioned, and I think it's very important, is that our notion of maximal update is not the same. So if we purely follow the μp prescription looking at neurons, how much the neurons change, we actually fail this criteria. This is very interesting. This is very interesting because we actually don't think that we can achieve theta 1 neuron update for our scaling. And the reason is actually pretty clear. It's a bit subtle, but it's actually pretty clear after we think about this for a second. Is basically these two cross kernels do not scale at law of large number scaling, right? They are actually scaled at central limit theorem scaling. So what this means is that we can get effects from the cross terms. For example, especially this guy, right? How much HL needs to be updated at a smaller order, right? A smaller update in HL can give us the same order of effect on the kernels, right? So this is essentially what is happening here, right? And then actually, let's go back a couple of slides. If you look at some of these terms, right, especially like these guys, this Q squared here, or this Q times RG here, right? So these guys set the scale a lot lower, right? So if these guys drive the dynamics, and Q is already non-trivial, RG is already non-trivial, right? It drives the dynamics in a way that smaller updates is actually sufficient to drive how much the feature kernels update, right? So this is essentially the reason why. And we can show that this is actually the maximum scale that we can handle in our scaling. Yeah?
That's interesting. I was going to ask,
yeah.
Like after a step, it was Q and the normal UP. So like the
yeah.
between H and G is like order n.
Yeah, exactly. So in MUP scaling, both of these need to be 1/n scaled. Yeah. So that's essentially the key difference here, and it's part of the reason why our kernels are not concentrating as well, right? So it's a bit of different scaling. And in our case, it turns out that the scale is, in fact, the scale of the SD updates or the SD terms. I didn't say here, but some of these initial conditions, especially if you don't train the first layer, are actually trivial. So you need RG to actually drive the dynamics. So RG also has a 0 initial condition. Well, but this guy will always increase to non-zero, and then once RG becomes non-zero, the rest of the dynamics starts to be driven by it. So there's a sense that RG does set the scale for R phi as well as phi dot, right? So it's a bit subtle. Yep.
So RG grows, but then it saturates?
It does not saturate. No, it can continue to grow. Yeah. So it grows linearly with tau. Yeah. Yeah. So this is depth time tau, right? So we think about you can imagine that this is kind of like how much of what's the percentage of the network that you have covered with RG. Right. So that's the way to think about this. Yeah. So it grows to say like if your tau bar is equal to 1, right? Then you're like, and tau is equal to like 0.5. You're halfway through the network of covering like what RG can be. Yeah. 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 So this guy can by the way you can this is because the RG doesn't show up on the right hand side. This is just an integral, right? So you can just write it as integral from 0 to tau. Yeah. Okay. So I do want to emphasize at the end of the day that our notion of maximal learning or feature learning is not a measure on the update scale of neurons, right? We're measuring us on kernels, right? So this does raise the question, well, if given there is hyperparameter transfers, and given that we are learning features, right, in a maximal sense, we're keeping as many terms as we can, should we be rethinking this about feature learning actually in terms of kernels rather than in terms of neurons, right? Because in mu-p, it's actually equivalent, right? But in our case, it's not. In our case, this is different, right? So it turns out that the scale on neurons is, for lack of a better word, not sufficiently fine-grained enough to determine whether or not you're learning features, right? You probably want to look at kernels instead, right? So this is something that it's a yet another message I kind of want to push with this talk. Yep.
Do you know if so if you're residual, or I guess it's not residual, but like if you had okay, maybe I'm thinking about the wrong architecture.
Yeah.
But does it satisfy the complete feature learning?
It does not. No. Yeah. Actually, I did that calculation as well. Yeah. So it's a very strange thing. Yeah. It does not. Yeah.
But the total NTK is moving. And
the total NTK is moving. All the
feature kernels.
That's right. All the feature kernels are moving because remember, right? Like the feature kernel, the change in the feature kernel delta phi is just r phi plus like phi dot, right? So the fact that r phi and phi dot are non-zero means that your feature kernel at every layer is non-zero. It's changing by non-zero amount, right? So you're getting like completely non-trivial feature learning, but it somehow does not satisfy these frameworks. Yeah, somehow it's very different. Yeah, yeah, we were very confused as well because we're writing these two papers at the same time, and and at some point when we wrote down complete feature learning definition, and Boris asked us, hey, wait, does this satisfy this? And we calculate this and it doesn't, and did we make a mistake? But no, it turns out it was fine. Yes.
So when you say it's like a notion of maximal learning,
Yep.
kernels rather than neurons, is that like straight up? Like maybe there's a orthogonal transformation in neurons, but then maybe like neuron times neuron transfer, it looks the same as it without that transformation.
That's a great point. Yeah. So in some ways, the kernel representation is weaker by exactly a factor of orthogonal transformation, right? So because you cannot tell the difference if you rotate orthogonally your data, for example, right? But besides that, I think it's fine. And I want to say the orthogonal transformation should be okay. And the reason is, if your output layer is initialized by a Gaussian, then your equivalent up to orthogonal matrix multiplication, right? So if you're like, it basically retains the same like distribution, right? If you know what I'm trying to say, like a Gaussian vector is equal to orthogonal matrix multiplied by a Gauss, like it's like another Gaussian vector, right? So you kind of get one for free in some sense. So I want to say it's not so problematic. But you would be right that it's not exactly the same as like keeping the neuron features. Yeah. Yeah, it's a good question. Yeah. Okay. I'll summarize now. So analyze scaling limits allows us to prescribe how to scale up architectures, right? And give estimates for hyperparameters. And in particular, this is the main work I wanted to highlight today is we're able to derive a system of 4 backward SDs that characterize one step of training, and we show that the scaling does have feature learning and hyperparameter transfer. Several existing scaling directions. We talked about the shape transformer. We can extend this. We can definitely test this on a bigger scale. I would like to see especially transfer on a bigger scale. I want to see more things done on for the scaling of the random matrix theory direction. Specifically, both nonlinearity, adding nonlinearity, which is very challenging, as well as one step of update. So now we have some theory for how training works. I would like to extend that. It is definitely possible to extend this to finitely many steps, like a DMFT equation. I think the math will be a bit more tricky. We have to figure out exactly what is the right form that we want the final equations to look like. That makes us more amenable to analysis. And even closed, really. So we have to be a bit careful, but it seems like the pieces are there. The tool, we have enough tools. There shouldn't be like a wall that will hit. Okay, with this, I want to thank you all for listening, and I'll be happy to take any questions.
Thanks for a great talk. I've got a bunch of questions in between. Let's see. Are there any more questions, Mufan?
I guess maybe like a very high level question. Like remember when this whole line of work kicked off, the claim was like, oh, like the finite case is very complicated. So maybe we can go to infinite case and that'll be much simpler, and then we can carry intuition back. And it kind of sounds like this is like turning on its head, where we're deciding that actually to analyze the infinite case, we have to preserve as much complexity from the finite model as possible.
Yeah, so that's a good point. Yeah, so I think you're definitely hitting a pain point in this line of work. Is that Blake, Louis Pierre, and myself have shown you guys equations that look fill up an entire page basically, and they're definitely not easy to analyze. And it happens that if you want to simplify this, you lose something, right? So. Is this simpler to analyze? I would still argue that it's simpler to literally analyze a finite size network. I think I would still argue that this is simpler, but it's more like the simpler result is not simple, right? It's not. It ends up being also not like easy to analyze. I mean. I think the hope is that we can understand the structure better, so that we can figure out ways to work with this better. And I mean, like, there are some things that ended up being amenable to analysis, right? Like, for example, the linear spectrum that I showed earlier, right? We were able to solve things to pretty satisfactory extent, I think, in my opinion, but it doesn't seem like, all the structures are going to yield, like, very simple, like, analysis. Yeah. So it's a good question. Yeah.